Okay, good. Okay, now it's okay. Okay, so what's the meaning of the model? I'm very sorry. So we talk about the what's meaning of the model. And then yeah, we talk about the current algebra, JA, Z, JBW is equal to Z minus W squared K over 2 delta AB plus I epsilon ABC JC W Z minus W. Okay? And if you take the residue from here, the bimodal expansion Z sum over ZAN JN JNB and is equal to I epsilon ABC JC M plus N. So this is the current algebra. This is an often called alpha and D algebra of SU2 SU2 part K. And the last time, so we define highest weight state. H sets up the J0 HJ HJ and then J0 plus HJ equals 0, and also JNA HJ, where n is greater than 0, a is any. So that's what we have defined last time. Okay. So it's recording, record it. I think it's better to make myself humiliated. Sorry, I came late, 25 minutes later than usual. And then to the subalgebra. So SU2 subalgebra, of course, zero mode. If you set, so then it's J0A, J0B is satisfied epsilon ABC, J0C. So this is subalgebra SL's SU2. Not hot. SU2 subalgebra. So this can be understood as the I mean, up to constant, you can just write down, of course, as you know, sigma A, sigma B. So power matrix is satisfied this algebra. Here. So this is called SU2, the algebra. The algebra I'm going to explain later. Moreover, if you define another set of the J1A is equal to J minus 1 plus, and J1 minus is equal to, sorry, J1 plus minus 3 is equal to J03 plus K over 2. Okay. If you define like this way, then you can have another copy of SU2 subalgebra. They satisfy the SU2 subalgebra. The algebra, the subalgebra. Such way that the, of course, as you know, J1 3 J plus minus 1 is equal to 2 J1 plus minus, and then of course J plus 1 and J minus 1 is equal to J1 3. So this is the another subalgebra, and we know SU2 representation, finite dimension representation. In representation will give you spin J representation. So it's always spin J. J runs for the spin J representation. Often it can be written as the states can be written as Jn, where n runs for minus j minus plus 1, j minus 1, and j. So this is the. So what is the dimension of spin J representation? 2j plus 1. Good. So m can run from minus j to j. So dimension of spin j is 2j plus 1. So this is finite dimensional representation, and often in Lie algebra textbook, the Young tableau, which is defined by 2j. So j is half integer. Usually j is half integer value, and of course spin 1/2 representation is of course as you two-dimensional. If you plug into here two-dimensional representation, it's just up state and down states. There's a plus state and minus state. They are related by j plus and j minus, and of course j3 plus is equal to like this way up to factor, yeah. Maybe in that definition, maybe 1/2, and minus 1/2. Okay, so this is the spin J representation. Spin 1/2. This is spin 1/2. So we know that the representation is this, do you need a 1/2 here? I don't remember. Or we just, this one is just satisfied. Just one minute. 1 minus I. So this is the states. No, I don't think you need a 1/2, I think. Yeah, I think you need a 1/2. Okay, good. So now, yes. So therefore, so this representation can act on. So this subalgebra acts on the highest weight states by spin J representation over there. Spin J representation. So therefore, so this is indeed it has to be the this has to be something like a J03 minus K over 2, right? Acts on Hj. And we know H03 acts on J really depends on acts on spin J representation. So this one should be also in the integer. So since this subalgebra should act on the highest weight state as a spin J representation, therefore this has to be half integer. So as you know, so spin J representation J3 is always some Jm is equal to m Jm. M is always half integer. So therefore, this has to be half integer. From here, k is integer, has to be integer. Okay. So this is the case. So k is integer. So this affine SU2 affine Lie algebra, you need a k has to be an integer, and then so from constraint by h square minus 2j plus k. So this last time at the end of the lecture, I derived this one. So from here, you can have j can be take up to k over 2 and a half integer. Okay. So this is a constraint coming from the unitarity and also the spin j representation. So therefore, so given the highest weight state, j can take up to k over 2 and a half integer. Unlike here, here j can take any value. On the other hand, for SU2 level case affine Lie algebra, you can take j can be up to k over 2. Okay, so this is the review of last time, and I will talk about a little bit in Lie algebra, Lie group and Lie algebra. Okay, so Lie group and Lie algebra. Lie algebra. Okay, so SU2 Lie algebra is the given by, as I mentioned, power matrix A is 1, 2, 3. We read to Lie algebra, SU2 Lie algebra, and we want to generalize this one to general a bit more. To do that, I will introduce the Lie group first. So Lie group, so is the indeed a manifold. Lie group G is indeed it should be manifold, essentially manifold with group structure. Means group structure. You can have manifold means you can have essentially you can have the group G is a manifold with group structure. So group is you can have multiplication and inverse and the identity operator. And the manifold has to be you can map to the logarithm open patch. So this can be done by just considering some metrics. So at this moment, even if you don't understand manifold group structure, you can just consider the example. For instance, GL. GLN is n by n matrix. F is a ground field. F is a ground field. Ground field which can be either R or C. In this lecture, so this Mn is an n by this is indeed n by n matrix, and then of course the determinant is non-zero. Non-zero. So therefore you can have a group structure, which means you can have inverse. So unless you don't have an inverse, you cannot create a group. So therefore, determinant has to be non-zero. And the special linear is the same thing, but the determinant A is equal to 1. So often yeah. Anyway, so and also symplectic gauge group. Symplectic group. Symplectic coming from the name Wow. Some Wow wrote a very classic book by a classical group. So he coined the name of symplectic GL to NF. But now we can have the AT JA is equal to J, where the J is equal to minus identity 0, 0. So this is a matrix. And often, so we call as O and F is the A is the same GL and F, but now AT A is equal to identity. So this is the also special orthogonal group, and also I have to impose usually in general determinant of A is equal to. So this is a condition, and often so this one is called carbon killing. There's a late 19th century carbon killing classified Lie algebra. This is called A type, and this one is called C type, and this one is called B or D. This is called Bn and some. No, this is Cn. This is B n over 2 if n is odd, and this is n over 2. This is n is even. So this is the carbon killing classification. Often there is such classification, and also you have a E 6, 7, 8, and G F4 and G2. So G2, which I'm not gonna explain because I'm not gonna use this lecture. So this is the carbon class killing classification. It's called carbon killing classification. So late 19th century. And in particular, if F is if you take F is equal to C, in fact, you can have a familiar group equal UN, which is the A is GL and C, and a dagger A is equal to 1. And if you put the special unitary condition, S means special, which means determinant is equal to 1. The same, the determinant A is equal to 1. Special unitary. And if you set n equal to 2, if you set n equal to 2, you can have SU2 gauge group, SU2 group. So, for instance, if you set n equal to 2, you have a SU2, which is something like a alpha, beta, where alpha beta is C, and the alpha square plus beta square is equal to 1. So for instance, you can have this kind of matrix. This is SU2 group. So then, if you take the Lie group real entry, so you have On. So family object orthogonal group, which is the A, G, L, and R. And then A is A transpose is equal to 1. And if you add, especially unitary component, speciality condition, you get SOM group. So this one will preserve. So these were the isometry of Rn with standard metric. Standard metric means d square s is equal to dx1 square plus dot 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 plus dxn. So this is the isometry of the Minkowski. Euclidean metric. Moreover, so this UN SUN is isometry. So these guys, the isometry of Cn and standard metric. D squared S is equal to dz1, dz1 bar plus dot 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 dzn, dz bar. These are isometry of the Hermitian metric of the complex space. Okay. Any questions so far? Okay. And Lie algebra. So if you have a manifold, you can always define. If you have a manifold, you can always define by tangent space manifold M, point P, TPM. So this is for tangent space. And many people here already took my course on the differential geometry course, but some have not. So you can just take a look at some textbook if you haven't. But so Lie algebra usually called G, or in Germanized G, is indeed the tangent space can be identified as a space is a vector space of identity. So there's a whatever G is kind of symmetric space. G, and there's the identity operator. So of course it's a group. It's a group. So there's the identity operator, and you just consider the vector space as a tangent space. Yep. So this is the T1 G. So this is a, of course you can have, so since it's just a vector space so far, but you can so vector space you have addition. To have algebra you have to introduce multiplication. Multiplication is essentially, so you can have a tangent space, tangent vector x1 or x2, and then so you can have Lie algebra, Lie bracket, sorry, x1, x2 minus x2, x1. What's the matrix? Tangent matrix. And then Lie algebra is indeed so vector space with this Lie bracket, and this Lie bracket plays the role of multiplication. So usually when you say algebra, you have addition and a multiplication. Addition is the addition as a vector space, and then multiplication is given by Lie bracket. So this is a bit abstract, but in practical, if you have a x in the algebra, then if you expose the map by exponential map, exponential g to g or gain to g, such that the x is mapped to, so mapped to e to the x. So this is the extensional map, which can be understood. I mean, you just do the Taylor expansion. Sum of L is equal to 1 plus x plus 2 factorial x squared plus x cubed plus 3 factorial. Like this one. So then, so example, okay, so then I can just use this white blackboard as the example. So if the algebra of GL is the indeed, you can just have any matrix. Any matrix. So if you exponentiate of any matrix, as you can easily see from here, we start with 1. 1 is of course identity matrix, and x can be x is a matrix, so therefore you can always have an inverse. And then so SL and F. SL and F is indeed the same thing, but determinant condition A. So determinant EX is equal to 1 becomes, you can just do the Taylor expansion and then look at the leading order. So determinant so determinant, so if you look at the determinant of EX, you essentially, this will reach you to trace of X has to be 0. So this can be understood as if you take the small, let's see, t is epsilon is very small parameter and epsilon is a very small parameter. Then essentially you have a 1 minus plus epsilon x matrix. And if you take determinant of this matrix, and you can see that this is equal to 1 plus trace of x. You can have trace of x. And the order of epsilon to the epsilon trace x. So therefore trace x has to be 0. So therefore it's determinant A equal to 1 condition is trace A has to be 0 in the algebra level. For symplectic, so usually you use the algebra for German letter, so SP or mass is called Maßsprach in later. So this condition can be changed in the following way. So it becomes linearized. AJ transpose or whatever dagger or transpose plus JX is equal to 0. So JA, thanks. JA is equal to 0. And then SO so here becomes again determinant A equal to 1 condition becomes trace A becomes 0 condition, and here you just have a T plus A equal to 0. So this is linearized condition for U, Oh, SU, it's the same. Yeah, so it's the same. So maybe I use SU, and so trace condition is indeed determinant condition becomes trace condition. On the other hand, a dagger plus A has to be 0. So this is 0. And likewise, if you use the SO, look at the SO. Determinant condition becomes trace condition, and then this becomes A transpose plus A has to be 0. So this is the determinant. This can be understood as you just do the Taylor expansion, and this condition is replaced by this condition at the level of the algebra. Okay, and in particular SU2, you can just do the following trick. Yes. Yeah.
It's not necessary to write the SO and F because you can only define SO of R.
I mean, it depends on notation. So, I mean, this is mathematician usually use for define the SO. F can be, in general, you can be quaternion field, and when F is equal to C, SO becomes essentially SU. But this is mathematician's way to define the SO. I mean, usually physicists only use call it SO, this is only R. But in general, so it depends on notation. So if you pick F is equal to C, it reduces the definition of SU. Another question is what? Yeah, trace A equal to 0. Thank you. And in particular, SU is matrix is the traceless, which means the alpha and the minus alpha. And then if you take dagger plus A, which is equal to 0, means that the beta, I have to be careful, minus beta. No, I think. Yeah, I think that's correct. So this is the alpha and the beta. This complex number. And then I think if you take a dagger and plus, you will get the. Am I? Get the 0? Yeah. So this is the condition for SU. So this is Lie algebra. And in particular, sorry, I think I told you wrong. It should be 3-dimensional, so this becomes 4-dimensional if it is the case. So therefore, beta is complex number, alpha is real number. This should be the case, right? Yeah. So this is SU2. And then of course, the basis is a vector space. There's a basis, so sigma x and I sigma y and I. Oh my goodness. Sorry, I think this is complex number, right? Sorry. Yeah. So if you take, it has to be purely imaginal, which means I times R. Yeah. So the basis is these guys. So the depends on notation. If you use I times sigma x. So this is familiar SU2 Lie algebra. So over maybe 2. So this is the SU2 Lie algebra. Okay. So it's a vector space. So as I mentioned, it's keep mentioned. So it's a vector space with multiplication by the bracket. So the dimension of the Lie algebra can be. So dimension of Lie algebra is the dimension of dimension as vector space. As a vector space, so therefore you can have the basis, usually TA. TA is a matrix which satisfies this kind of condition. A runs for 1, 2 dimension G. And in particular, physicists, you can always take the trace of TA and TB. Can be 1/2 delta AB. We can always take this kind of basis. It's called Cartan killing form. And in particular, so any element x in G or K can be written sum over XA, TA. Okay, XA is some number. So therefore, XA, XY can be written as TA, TB, like this way. And since it's a basis of vector field, vector space, so therefore this TA, TB, the Lie bracket can be always written in terms of the another matrix TC, F, ABC. Sum of C. So it's a vector space, and the TA is a basis. So therefore, Lie bracket with these two elements can be written always as a linear combination of another the basis. This is the meaning of this. And often, so this ABC is called a structure constant. Structure constant. In my lecture note, I multiply I here. I here. And then, yeah. And this Lie bracket has a following property. So Lie bracket has a following property. So Lie bracket is in essentially G goes to G, and one is bilinear, which means that the x plus by and c is equal to a x z plus b y z. So this is the bilinearity, and antisymmetry is the essentially xy is equal to minus 1x, and then Jacobi identity which is xyz plus yzx plus xy is equal to z. and from here you can just conclude that the FABC is equal to minus FBAC, and from here one can have the following Jacobianity FABC FCDE plus F, and so it's structure constant should satisfy the following. FDA C FCDE plus FBDC FCNE equals 0. Structure constant should satisfy this condition. Okay, so this is a classical of Lie algebra and Lie group. And now we have so this is G is a finite dimensional condition now. Dimensional vector space. Vector space, but now we will generalize to infinite dimensional. Infinite dimensional case, and this is the typo I FABC. So FABC is the structure constant Jn plus n c. But now n and n can take any integer value, so therefore the infinite many generator is the finite many generator. And when so do the so-called if the delta n plus n is 0, do the levels appear. Okay. So this is called G hat k. G hat k, and it's called the affine Lie algebra. Affine G Lie algebra with level k. Okay. Thank you very much. So here you have n delta n equal to 0. Okay, so this is the crash course of Lie algebra and just affinization. You just bring the infinite many copy of a generator of Lie algebra and then satisfy this condition. So that's affine Lie algebra. Any questions so far? Okay, let's go to West-Lemino-Witt model. Novikov-Witt model. Let me see this. So now, the last time, so we consider action U1 West-Lemino-Witt model, or free boson can be formulated. Free boson can be formulated S is equal to so S is equal to, I forgot how I formulate, some number times d squared z, partial g, and partial log g. That's what I have done last time. Inverse actually, inverse, where g is a map from the complex plane to the S1 or U1. And we want to replace this action by C to any Lie group G. So that's what we want to formulate. So then, so to do that, we start with the just mimicking this action. So we just G is a map from the complex plane to G, or in general, so some Riemann surface to G in general, whichever is okay. And now, so we can have this kind of action, or more generally, so some number times d square x, which will mean G like this way. And the G is now it's not U1, and then if it is not U1, we will show this not this action is not consistent as a quantum field theory. To see that, so I call it this is 1 over 2a squared. This is 1 over. It's the 2a squared. And do the following trick. We want to take the variation with respect to G goes to delta G. Okay. G plus delta G. Variation G plus delta G. And then what is the action? So delta S, how's the variation of the delta Z? Delta S. So this is the important step. So this important step to use the next homework. Trace of inverse, and we want to take variation with respect to. Okay, so this can be written as 1 over 2a squared d squared x, and as you know, so G inverse G is always 1. Okay, so this is a group structure, and this has to use. So if you take the derivative G inverse G plus, if you use it, you just use Leibniz rule, mu G equal to 0, and then this becomes the partial mu G inverse can be written as G inverse, minus G inverse partial mu G and G inverse. Okay. This is likewise. So this you have to use some homework next week. So it's an important step. Anyway, everybody can figure out. And also, likewise, delta G inverse can be written as G inverse delta G G inverse. So therefore, action can be written as the following way. So this is minus. So minus trace. Oh, sorry, I didn't put the trace. Did I take a trace? Okay, sorry. The action. Sorry, I made lots of mistake. So now it's a non-abelian game. G is non-abelian. Non-abelian means the element G1, G2, G1, G2 is not equal to G2, G1. Okay? So it's now it's a Lie group, and the if G is not U1, it's a non-abelian gauge curve, non-commutative. It's a matrix value, so it's no longer a commute. And so therefore, you have to take a trace to be gauge invariant. Sorry, I have to use trace to the gauge invariant. So you have to define a gauge invariant action. Gauge invariant means the G goes to whatever H inverse. So the H is any group G. So this is adjoint action. It's a gauge transformation, and in order for the action to be gauge invariant, this has to be the case. Yeah, I think so. I'm correct. Yep. So you have to use trace condition. So then, if you use this condition, trace, then this is G inverse partial mu G, and G inverse partial mu G. So this is a action of the yeah, so this is the action, and now from here we want to take a variation with respect to this. So to do that, I already forgot what I should do. So to do that, I think delta. So yes, last night I think. Sorry, just a moment. So this is important part actually indeed. Last night I did this computation before I sleep, and then I slept over. Okay, good. So now, important part is that you can have a repeated, right? So you can have G inverse partial mu G, G inverse partial mu G. Okay, and take so therefore delta of S can be understood as the minus delta G inverse partial mu G, G inverse partial mu G. Okay, and you have 2 is gone. Okay, do you understand? So you have a 2 copy of them, and take the variation. You can just take one of them and multiply by 2. Okay, multiply by 2. And then this is equal to minus 1 over a square d square x. Delta G inverse is satisfied this one, so therefore you have a plus sign, and trace G inverse delta G, G inverse, and partial mu G, and G inverse partial mu G. So that's one piece. And to do the Leibniz rule, trace G inverse partial mu delta G, G inverse delta mu G. Okay. So this is a case. I think it's unfair to do the sign change simultaneously. Therefore, minus 1, and here it's minus. Do you agree? Do you agree? Is it okay? So I just use the Leibniz del G inverse is I just use this one, this guy. This is kind of complicated, but you have to do that. And plug this one into here. On the other hand, del can act on here, this guy, and then you can have a second one. Okay, and then what should I do? So this is equal to So this is equal to 1 over s squared d squared x in trace, and then partial mu g inverse delta g, and then g inverse partial mu g. Do you agree? G inverse delta g. Yeah. So let's take a look why this is the case. If this guy acts on delta g, you have this guy, right? Why I not delta? The partial. Partial. Are you guys following? So if this derivative acts on delta g, you get this guy. Okay. If the derivative acts on g inverse, you have to use this guy, okay, to get the upstairs. Can you see that? Can you see? This is the case. What? Can you see that? So it's trace. So you can see, can you see it? So you can bring this guy into here, right? But inside a trace, okay? So if you bring this guy into here, if you use this relation, you get this one, okay? So if you bring this guy into here, you have a G inverse del G G inverse, which is derivative acts on G inverse, okay? And then the rest piece is the same. This piece is the same. Okay? So and the minus sign is here. Okay, so therefore this is equal to 1 over a squared d squared x. And do the integral by parts. You can just have a 1 minus a squared d squared x trace g inverse del g, and then partial mu g inverse partial mu g. Okay. So this is the after integral by parts. So this is the variation of the action. Okay. So therefore, you can just conclude that the current, the equation of motion has to be partial mu g inverse partial mu g. So this is the equation of motion under this variation. And in particular, if you define the J mu G inverse partial mu G, so this can be understood the current conservation law. But however, if you use the homomorphic anti-homomorphic coordinate, you can just have J Z. So this can be understood or homomorphically. So you just define J Z as G inverse G, and J Z bar is G inverse G, and this can be understood J Z. So this is the current conservation law. And for U1, it's unlikely. It's very different from the U1 case. So U1 case, you can have also, so let's see, JZ can be understood as the phi, like this way, as you recall. And you can have the current conservation is like this way. You just impose holomorphic condition. So in the case of U1, is CF U1 free bosons. So it's a bit different. So you cannot factorize from holomorphic and anti-holomorphic currents. So you need to do some extra trick to do the current conservation in holomorphic and anti-holomorphic way. So to do that, you need to include some action. You need to change this action a little bit. So the way to change the action, I will tell after the break. And I'm very sorry about being late. So let's take a 10 minutes break. Question?
Is this nonlinear sigma model, can we understand it as a kind of gauge theory, where G is a gauge extension?
I don't think so. Gauge series means if you have a connection, you should modify mu, and this mu is the.
Yes.
But here, derivative is just ordinary derivative.
Then why you said we need to maintain the gauging values by taking the trace?
Good question.
We wrote G to HG H inverse.
Good question. So it's not gauge theory. Gauge theory means you need a action like a F mu type of term.
Yes, indeed.
But here there's a gauge transformation, so that the gauge transformation is really G mapped to C equals to G. So this G is a map. So this is really a linear sigma model.
Yes.
And the gauge transformation is the any H in G, HG inverse HG inverse is a gauge transformation. So this is a gauge transformation. Why this has to be the case? If you want to consider if you want to consider path integral of this, you have to impose this equivalence. I already forgot why this is the case. But don't you think this is natural gauge transformation?
Yes, it's very natural.
Very natural, right?
It's called gauge transformation, but it's not really the gauge transformation in gauge theory.
Yeah, it's. I mean, F mu nu F is transformed by gauge transform G inverse, right? On the other hand, A is transformed like a G inverse dG plus G inverse A dG, right?
Right.
And then, I mean, F mu nu is more or less like the nonlinear amount of Mach G. I mean, yeah. I mean, of course, F takes the value of Lie algebra now, but here you take the value of Lie group. Yeah. I don't know. I mean, there must be more intrinsic explanation, but very natural, right? This is gauge transformation. I don't have a immediate answer why this should be the case. I'll take a look at it later. Okay, shall we resume? Okay, now, so we're going to modify this action over there. To modify the action, so we add, so S is the ordinary time. So let's call S, I call it S0 maybe. I call it this S0. S0 plus some term which is called K times minus IK over 12 pi. Of course, K is the one up here before, but I will explain why this is the case. And then essentially dqy is on alpha, beta, gamma. Trace. Now, what is B? So, okay, G tilde inverse pressure. So this is the action we will do. So now I'll explain what B is. So now the previous case we consider the map from the Riemann surface or C, whatever, Riemann surface sigma to G, Lie group G. So sigma is a Riemann surface, two-dimensional Riemann surface, and now B is a three manifold. Which bounds the sigma. So it's a three-dimensional manifold B whose boundary is two-dimensional Riemann surface sigma. And in particular, so we have the map from G goes to sigma goes to G, and then we extend this map by, and if you restrict yourself on sigma, this becomes G. That's the action we will consider. So G tilde is the extension to the three manifold of the map G. Why people is it consistent? So first of all, there's ambiguity, how to extend G tilde, and also the choice of B. There are lots of three manifold which bounds the sigma. There are lots of. And why this action is consistent, you have to consider. Okay. So in order for this action to be well defined, so you can also consider the following another extension. So you can also consider another extension B tilde and G whatever G prime, G tilde prime, which is B prime goes to G. So you can consider. And now you can have the cross-free manifold, which is the cross-free manifold is B sigma minus B prime. Minus B prime, it means that you take the orientation reverse. Minus B prime. So if you how to say compose B and B prime along this sigma, if you group them together, you get the cross-free manifold. And then you can have in a map from G tilde, I call abusing notation, I call G tilde to three manifold G. By just restrict yourself on B, you use this G tilde, and B on B prime, you use this G tilde prime. You can just compose them. And this action can be written as the essentially some number. So this I call this part is K gamma. So K gamma can be written as K times trace G to the inverse D G which G to the inverse dg, which G to the inverse dg to the. So like this way. And if you take my differential geometry course, this is known by Maurer-Cartan form. This is known by Maurer-Cartan form. Of so essentially, so we just do the following. So you have a map G tilde. So okay, let's call M3 maybe. So let's call this is M3 maybe, and manifold, three-dimensional cross manifold. And you have a Maurer-Cartan form. Theta is equal to G inverse dg. This is Maurer-Cartan form. One form of G. And then, in fact, if you take the trace, okay, like this way, then this is an element. You can show that this mathematically. This is third cohomology group of G. As you keep repeating, G is a manifold, so you can consider the homology theory or cohomology theory, and then which takes the integer value. Integer value. So this is the most important point. So here it's a cohomology of integer value. So you can show that this is the case, and then since it's a map, G tilde is the G tilde is M3 equals to G Smith map. Therefore, in fact, the gamma is indeed the pullback of this Maurer-Cartan form. Let's go pullback of Maurer-Cartan form, which theta. Pullback means there is a map from manifold M3, so this is M3 to G. M3 to the G is another manifold. G is very symmetrical. Let's go like this. This is G tilde, and there are three third cohomology, integer cohomology, element, and they just pull back to the M3. So this is the gamma is really the pullback of third cohomology element. So therefore, this has to be the usual cohomology theory M3 of integer body. Therefore, its integer body means that if you integrate over this action, I wouldn't. I think I'm abusing notation. I didn't. Okay, I think I should. Okay, I should call it gamma indeed. So gamma is actually already integrated. So this is not gamma actually. Gamma is actually integral over b, so I shouldn't call it gamma in b. So maybe let's keep it as it is. So this part. I think I should call this part. This part is up to constant is equal to this one. Okay? Up to constant. I didn't integrate over. And then so this one, so I shouldn't call it gamma. So this guy is indeed the pullback of these three cohomology integer values element into the M3. Therefore, if you integrate over gamma, integrate over M3, so this element k, and trace G tilde inverse the G tilde and the three copy of them. This has to be equal to k times integer. Okay? K times integer. Some number, integer. Depends on the G tilde. Over M3. So this is what it means. So so integer value means that if you integrate over this cohomology element over M3, you have to get the integer value. So it's a pairing between third homology group, integral homology group, and a third integral cohomology group. Okay, so it's a pairing between them. So you should get the integer. So this is the most important part of this the action. So therefore, k. So since the action in quantum field theory, the action will appear e to the minus k gamma. Gamma means this piece. This piece gamma. And in order for this action to be well defined, independent of choice of b or b prime, if this is 2 pi I k. Okay, I think I should call. I think I should call this one is 2 pi and 2 pi I. Sorry. Yeah. What should I do? No, what I'm doing here. So it has to be. What I meant is 2 pi I k times gamma. I think what I want is this kind of stuff. Okay, 2 pi I times k times gamma. So therefore we know gamma is integer value. So therefore k has to be integer value in order for the action to be well defined. Okay, do you understand? If this is the k, so it has to be 1 in order for the action to be well defined. So if this is 1, it's independent choice of b and b prime. Okay? So difference is you cannot see the difference between b and b prime because it's just the difference is just 1. Okay? So therefore, this from here, k has to be integer. So this is a condition you will get from this with similar term. I'm not careful about the question at all, but everything is well defined. If you are careful about the question. So now you can consider so now we understand this action S is equal to S0 plus k gamma is indeed K gamma is well defined, independent of choice of B and B prime and the extension. If you take the K has the K is integer. Now, and often this term is called Wess-Zumino term. So this action is called Wess-Zumino. Or Wess-Zumino Witten term. And then we would like to play the same game. So it was as before. So under the variation G plus delta G. So what is the delta S? And this is homework. This is side generation, what I have done before. So it's delta S0 plus I over IK for phi. Unfortunately, I cannot write down. Maybe let's squeeze. Okay. So this is you have to take the variation with respect to whatever G. I mean now I call it G tilde is equal to G by abusing notation. So under the variation, you have to show this variation action of a similar term is the you get this. This is a homework. It's kind of a bit tedious, but you have to do a slightly generalization of what I have done before in the first lecture, first part of the lecture. And from here, one can have partial mu T inverse equation motion is indeed a square IK divided by 4 pi with some mu. Like this way. So this part coming from S0 and this part coming from Wess-Zumino term. Essentially, S0 is actually a kinetic term, and this term is the more or less topological term or Wess-Zumino term. And this is the equation of motion, and this can be written in homomorphic and anti-homomorphic language. This can be written as 1 plus a squared k over 4 pi. So this equation motion can be written in homomorphic and anti-homomorphic language. And now we can have the if you set a square is equal to 4 pi over k, then you can have an equation motion as we desire. Okay, so this is homomorphic current, and this is anti-homomorphic current. Anti-homomorphic current. Then at the end of the day, action if you obtain this kind of action, holomorphic antihomorphic current, we need K over 8 pi d square x trace of operation mu G inverse operation mu G and plus K times gamma. K times gamma. So this is the Witten action, Witten-Norvico Witten action. And then, as you can easily imagine, that this homomorphic antihomorphic current is associated to this current algebra I introduced before. Any questions so far?
If we perform gauge transformation usually simultaneously, then it will we can turn it naturally twice.
Yeah.
And in that case, G is the element of the algebra instead of the group.
Why? So in my lecture, the differential geometry course, there's a homework in the last homework I gave. So you consider the transaminase action K over 4 pi and 3 trace A which the ADA plus 2/3 A cube, and if M3 has a boundary, and the gauge transformation A goes to G inverse dA, so dG plus G inverse A G. So now G takes the body of Lie group, right? And then this will give you, I already forgot, delta S transaminase is indeed equal to plus and 3, I forgot to K over some 4 pi or 8 pi, I already forgot some number, plus trace of G inverse dG cube, that's what you get. And also you have, I think, the same coefficient, I forgot the K over 8 pi, K over 8 pi of sigma and trace of, I think, G inverse dG which A, I think that's what I remember, something like that. So what's the Witten term? And if you impose GA as a pure gauge, you get the what's the Witten action. So in this case, G is really element of Lie group, right? I mean here A is a Lie algebra, but G is Lie group. Takes a Lie group. Yes. Yeah. I mean, you can G minus dG can be understood as pure gauge. Yeah. Yeah. It's in two-dimensional language. It becomes current algebra. So here, this guy takes the body of Lie algebra. But G takes the body of Lie group. Okay. Any other questions? So we will try to obtain Okay, now so we define from now on. So we define JZ homomorphic current as the minus K over 2 times JZ over the JZ is this one G inverse G, and J bar C is equal to K over 2 G inverse bar G. So we define like this way, and of course what we're going to do is indeed J Z is equal to sum over J A Z and T A. A runs for 1 two-dimensional Lie group. Liaison, whichever call it, J bar Z bar. Oh, sorry, I think it's Z bar. Z bar. Can be expand as J A bar Z bar Z A runs for 1 2 in G, and as we will derive in the rest of the lecture it satisfies the current algebra. J A of Z J B of W is indeed, as we expect, the current algebra. I forgot K over 2 delta AB Z minus W squared plus I F A B C J C of W as a OPE over Z minus W as a OPE. So that's what we're going to do. So therefore, from with the model, you can obtain affine Lie algebra, or the symmetry of affine Lie algebra naturally arise from with the model. That's what we're going to do from now. And yeah, so the reason why we add this with the term is to get the really this homomorphic anti-homomorphic current J and J bar Z up to this correction of K over 2. Correction K over 2, and then since it's a Lie algebra value, so you can expand. So it's a matrix value. Expand in terms of the basis of Lie algebra TA I introduced just before, and then sorry, I think. Then, so this J satisfies this current algebra. That's what we're going to show. Okay, to do that, so we take the following so let's see. To do that, let's take the following. So in fact, so we have the equation motion over there, means that the G of so it's a Z bar can be factorized. GL of Z and GR of Z bar, as you can see, and then if you plug that one into there, you can just like for instance G inverse, whatever partial G can be understood as the GL inverse GR, and then partial GL and GR. Okay. GR. So now for inverse. And then so therefore, if you take the what I'm doing here. Sorry, I got confused. Sorry. So let's first consider the okay, the anti-homomorphic part, then you get the GR inverse GL inverse GL, and anti-homomorphic acts on only this guy. You will get the cancellation, and you have GR inverse partial about GR. Okay, so this is what we get, and this is equal to 0. On the other hand, oh my goodness, that's why I made a mistake. Sorry. You guys should tell me. This is anti-homomorphic current is okay, but the homomorphic current is the other way around. I already erased. I think I wrote the wrong thing. Sorry, I think that's why I made a mistake. Anti-homomorphic current is the other one. You can just have a partial G of G inverse. So you can have this way, yeah. Sorry. So then, so this has to be also opposite. Sorry. This is the opposite. And then you can have, yeah, so partial G inverse is equal to, you can just do the same exercise, partial GL only acts on GR, and GR inverse GL, which is GL. Sorry, what I'm doing here is inverse, like this way. Yeah. Is it okay? Yeah. So you can have the factorization. It's consistent. Factorization like this way. If you define like this way. And now you can have the you can consider under the gauge transformation I introduced us, G inverse is equal to omega of C G bar, omega bar inverse G bar, where omega takes the body of Lie group G, and then you can take infinitesimal transformation. Omega can be understood as an infinitesimal transformation, and then omega bar is also infinitesimal transformation. Omega bar. Then we can just consider the homomorphic part, and then the homomorphic part of this gauge transformation is something like a G plus omega G, and then omega minus G omega. This is the infinitesimal transformation, and I call this one is homomorphic part delta G, and this is indeed homomorphic transformation and anti-homomorphic transformation delta omega G. So, and we know delta S can be written as k over pi over sigma d squared of x. The important part is the variation. So you have to show in the homework, and this is equal to trace of G inverse delta G And then unfortunately I have to squeeze again partial G inverse partial bar and G. So the important part is even though the West Zumino act with the action, so the very important part. So you have to, this is a homework. Homework. So if you take variation, you use the three-dimensional West Zumino term, right? So we add B is three-dimensional term trace of G inverse dGq, essentially, with some number. So West Zumino with the action involves this three-dimensional part, but if you take the variation, it only involves only sigma. Okay? That's the most important part. Important part. And then if you take variation, then and if you plug that one into here, then we have k over pi sigma d square x and trace omega of z. So now you can plug this one into here, and what you get is the and this is also homework. You have to show this derivation is the essentially main part of the homework next week. Trace of omega bar of minus z partial z partial G inverse. Okay. So this is if you use this variation and plug that into here, you should get this one. So this part is very obvious, right? This part is very obvious. The second term is very obvious, but the first part you have to be a bit manipulation. You have to do the bit manipulation to get this one. Okay. I don't want to erase this part, so let's keep. Oh, by the way, so this I already erased the Chern-Simons and the relation between Chern-Simons and also West Zumino-Witten term. It's often called bulk edge correspondence in condensed matter physics. In bulk, you have a topological quantum field theory. At the edge, you have some which is topological, but at the edge you have some physical degrees of freedom, which is described with Zumino-Witten model. That's called bulk edge correspondence in condensed matter physics. So edge mode is described by West Zumino-Witten theory. So it's a very relevant in condensed matter physics. And then now, so we just rewrite this variation with respect to delta S as the, so it's a gauge transformation we're doing. I'm doing gauge transformation, and then variation under gauge transformation, the action has to be the following. So the minus 2 over pi over sigma d square x, and then you can have the trace omega z jz so yeah, you can use the integral by parts since we know yeah, anyway. So this is what you get by using the current using defining here. Okay. Yes. So we can rewrite this. So since the del bar doesn't see this omega, so you can rewrite this variation in this way. Okay. So now, so by using the Stokes theorem, delta omega bar omega bar s can be written as the minus I. Sorry, so this d square x is indeed minus I over 2 dz and dz bar. So then apply Stokes theorem, what you get is the I over 2 pi dz trace omega z jz plus minus I over pi dz bar trace omega bar z bar and j bar z bar like this way. Is it okay? Is this funny? Is there something wrong? Is something wrong here? Okay, so now, so the form really looks like a Ward-Takahashi identity. So now, so we can just have the so delta x, so the correlation function, so it's a really like a Ward-Takahashi identity. So we can use the Ward-Takahashi identity for correlation function delta omega bar x is equal to so delta s x. So therefore this can be written as minus 2 pi I dz sum of omega a ja of x, and then plus 2 pi I dz bar corresponding Ward-Takahashi identity is the a omega bar a ja x. Okay, so this is a case, and then so this is corresponding Ward-Takahashi identity. So since we know that this gauge transformation symmetry of the action corresponding to Ward-Takahashi identity, this is Ward-Takahashi identity is this guy. So now, and also we know that the transformation omega of j is just gauge transformation, is indeed omega of j. So we know that here j transform so just plug so g is transformed by omega anyway, so g is transformed on the g plus delta omega g plus delta omega bar g, and then plug that one into here. Essentially what you get is indeed and then here is you have homomorphic one omega g, and this is delta omega minus g omega bar, right? That's what we have. And plug this one into here, And what you get is that the omega delta omega j is equal to minus k over 2 delta, homomorphic derivative of omega. So, and also correspondingly the anti-homomorphic part. I'm not going to write. And then in terms of Lie algebra, we can just have this is delta omega. The basis, you can just have this can be written as some I times f abc omega b jc and minus k over 2 homomorphic derivative omega a. Okay, and then plug that one into here. Plug this one into here. What you get in the current algebra, we should get in the current algebra. So what we want is the delta omega bar of j a is indeed equal to you have to use minus 2 pi I delta dc and then sum of sorry I missed a here. So instead of a now I have to use b omega a omega b jb and ja. Okay. So this is the and then on the homomorphic part dz bar b omega b jb ja like this one. Okay. And then so we know variation has to be. So from using this as gauge transformation, we know the answer should be this one. Okay, the answer should be this one. So therefore, answer should be this one. So therefore, to compare between them, and also as you know, delta omega bar ja is something like a anti-homomorphic minus I f abc bar b j bar c. And minus k over 2 omega bar a. So that's what you need to what you should get from sorry, I think you need a bar everywhere. Bar here. I think here and also I think I made a mistake. There must be bar here, bar here. So therefore, you should get the bar and the bar here, or j here. Okay. I mean, if you want to get the j bar, I mean, you can have j bar part also. So you can replace ja bar and you put the bar here. And then compare between this guy and the variation of this one. So you get the conclusion that the JA of T, so you just need OP here, right? Of course. You guys doing lots of time about this kind of exercise already. K over 2 delta AB and Z minus W square plus IFABC JC of W and Z minus W. That's the conclusions you should get. So as you can easily see, this term, if you do the contour integral, you just get the JC and ABC. So therefore you get this term. And then so if you do the contour, plug this one into here and then contour integral. So this will give you the first derivative, right? First derivative because it's second order pole. Second order pole will give you first derivative of omega. That will give you second term. Okay? Second term. And the k over 2 will give you this. Okay. So that's what Takahashi identity will tell us how this current algebra, OP or current algebra. So this is the Walter-Gaussianity conclusion of Walter-Gaussianity. Okay, so this is current algebra, and so that's what we have seen before. And of course, we can have. I mean, here it's of course the dimension, conformal dimension current is of course 1, right? Because it's G and G inverse is dimensionless, and this is derivative has a conformal dimension 1. So therefore, you can have the mono expansion like this way, JA, and the n plus 1 like this way, and then from here you can have a finally algebra mono expansion. And k over 2 times L delta AB delta n plus m. So that's what you get from the just contour integral. I mean this is exactly. I mean TTOP give you Beer's algebra, right? TTOP it's like then current algebra will give you a finally algebra. Okay, so that's conclusion coming from the Walter-Gaussianity for gauge transformation of the Western Witten. Any questions so far? Okay. And this week homework you have to use T. This T of Z of SU2, and you have to use the following: 1 over K plus 2 sum over JA normal order C. So this is the you have to use the homework to use this. This is the Gawara construction of the Western-Witten model. So this is the, and then you have to show. This week homework is you have to show by using this form. You have to show really L naught. L naught acts on this highest weight state is indeed J plus 1, J plus 2, H and J. This is very natural because as you learn, if you learn quantum mechanics, you have JA acts on the state J, you get the J and J plus 1, right? This is what you have learned in the JA is essentially JX plus JY and JY and then J plus minus. That's easy to. So this maybe minus plus, I don't remember anyway. So you understand. If you act on this Casimir highest weight state, you get the J times J plus 1. So this is affine D algebra version of the statement. Okay, so that's the homework of this week, and then next week I will, finish the Western term and also rational conformal field theory and concept model, and then move on to integrable system next week. Okay, let's stop here. I can just stop recording.